What role do neural networks play in Neurotech decoding? Imagine a world where your thoughts could control a robotic arm or a computer screen without you saying a word. That's the promise of neurotechnology, and neural networks are at the heart of making it happen. These computer models are inspired by how our brains work, and they help decode signals from the brain into understandable commands. They process complex data like electroencephalogram signals or recordings from brain implants, finding patterns that tell us what a person is thinking, feeling, or intending to do. This decoding process is what makes brain-computer interfaces possible, allowing direct communication between the brain and external devices. Neural networks take raw neural data, which can be noisy and hard to interpret, and clean it up through a series of steps. First, they pre-process the signals to remove any background noise. Then they extract key features that are most relevant to understanding the brain activity. These features are fed into the neural network, which learns to classify or predict what the signals mean. For example, a neural network might recognize patterns that indicate someone wants to move their hand or speak. This ability to translate brain signals into commands is what powers neuroprosthetic devices, helping people with paralysis control robotic limbs or wheelchairs just by thinking about movement. In addition to controlling devices, neural networks are also used in diagnosing brain disorders. They analyze brain scans and activity data to spot early signs of conditions like Alzheimer's disease, Parkinson's disease, or epilepsy. Because neural networks can recognize subtle and complex patterns that might be missed by traditional methods, they improve early detection and treatment planning. Advances in deep learning, a type of neural network with many layers, have made decoding even more accurate. Convolutional neural networks, for example, can understand the spatial and temporal relationships in brain signals, capturing how different brain regions work together during movement or thought processes. Transfer learning allows these models to adapt from one person to another, which is important because brain signals vary greatly between individuals. There's also exciting progress in neuromorphic computing, which creates hardware that mimics how the brain processes information. These systems can perform real-time decoding with less power, making them ideal for implantable devices that need to operate for long periods without recharging. Overall, neural networks are transforming neurotechnology by turning complex brain signals into meaningful information. They help people regain mobility, communicate, and even detect diseases early. As AI continues to evolve, neural networks will become even better at decoding the brain, opening new doors for the future of brain-machine interaction and neurotech development.